Hello and welcome to our talk. My name is Nima and I'm going to be presenting our paper about SimFaaS, a performance simulator for serverless computing platforms. I'm a PhD student at the University of Alberta, and the other co-author of this paper is Dr. Hamzeh Khazaei, who is a professor at York University and is also my supervisor. The work done for this paper has taken place at PAX Lab, or Performant and Available Computing Systems Lab at York University. And you can also see the information about the paper on the bottom left corner of the screen. So today we're going to first discuss, have an introduction to the work that has taken place here, what the motivation for our work is. Then we will see the description of the system that is being simulated in our platform, SimFaaS. And then we will take a look at the design of the SimFaaS and some details about how it has been designed. Then we will see some sample use cases for the simulator, and then we will have the experimental validation of the platform, and then we will conclude our talk. So first up, introduction. So serverless computing is a cloud-native deployment model. And in serverless computing, developers build and run applications on the cloud. They pay only for the resources that are used instead of the provisioned resources. And it's an event-driven execution model. In serverless computing, runtime operation and management is delegated to the provider. So there's less overhead for deploying a workload by the developer. And you delegate tasks like provisioning and scaling of resources completely to the provider. And in serverless computing paradigm, software is developed by writing functions that have well-defined interfaces and are deployed separately. So this is a typical developer workflow of serverless computing platforms. So you upload your code to AWS Lambda or whatever your serverless platform is, and then you set up triggers that will cause the execution of your code, and whenever those triggers happen, your code will get executed by the serverless provider, and they will also take care of any provisioning and any other tasks that need to happen before your work is executed. And you only pay for the compute resources that you actually use, not the resources that was provisioned for you. And a performance simulator is necessary for the current generation of serverless computing platforms. First of all, no previous work has been done that accurately captures the unique dynamics of the modern serverless computing platforms. So there's no platform out there that captures every single thing about those and gives you a very accurate estimate for serverless computing platforms. An accurate performance simulation can be beneficial in many ways. It can help you ensure the quality of service. It can help you improve performance metrics. It can help you predict and optimize the infrastructure cost and move from best effort basis to performance guarantees. And it can be beneficial both to the provider and the developers and the users of the serverless platform. It allows performance prediction when you don't have any performance model, but at the same time, it can help you develop performance models. Now, this brings us to the system description, where we talk about the details of the system that is currently being simulated by SimFaaS. But keep in mind that all of our designs are extendable, so you can try changing them for new design ideas. So first of all, we need to define a few things. For example, we have function instances which act as tiny servers that will process incoming requests. And those function instances can have three states. Initializing, where they do some initialization tasks like connecting to the database, downloading something from an S3 bucket, or even loading a module into memory. Then they go into the running state, where they're processing a request that has come in. And after the processing of the request has been done, they go into the idle state, and they remain in idle state for some time to be able to handle incoming requests in future. And after some time, if there are no incoming requests for that specific instance, it will get terminated, and the resources that it has been consumed will be released to the system. From the perspective of requests, we have cold start and warm start requests. And generally, if a request comes in and there are no idle instances in our platform, they will need to wait for one function instance to be created and added to our pool. And then that function instance, after being created, can start working on that request. And this causes in a cold start request. But if we have an idle instance and a new request comes in, that idle instance can start working on that request immediately, which is what we call a warm start request. And cold start requests can be orders of magnitude longer than warm start requests. And that is why we need to always make sure that there are not many cold start requests, because they might affect the quality of service for our system. When we talk about auto-scaling of serverless computing platforms, here we generally try to talk about the scale per request platforms, which are the mainstream serverless computing auto-scaling functionality that is used in platforms like AWS Lambda, Azure Functions, or Google Cloud Functions. And when in a scale per request auto scaling, we have to talk about the scaling in and the scaling out actions. So for scaling out actions, we need to see how new function instances will be added to our pool. And the way that these systems work is that when a new request comes in and we don't have any capacity in our warm pool, we don't have any idle instances, that request will cause the creation of a new function instance. And then later on, that function instance will be added to our pool of resources. And this is how new function instances will be added to our platform. Now, about when we talk about the scaling in, this is typically when after some time the number of arriving requests has gone down, and some of those function instances stop receiving new requests. And after some time of not receiving any requests, which we call expiration threshold here, the server will be expired, it will be terminated, and the resources that it has been consuming will be released for other function instances. So this expiration threshold is a very important indicator of how the serverless auto-scaling is happening in a scale per request auto-scaling platform. Now, we want to talk about the design of SimFaaS and how it has been designed to allow the simulation of these kind of platforms. So this is the package diagram of SimFaaS, and we have utility functionalities. We have the simulated process, which also allows you to give it an analytical performance model, and it can compare PDF and CDF of the data from simulation to the analytical performance model that you have given it, which helps us to develop newly and more accurate performance models using our simulators. Then we have the function instance, which simulates the behavior of a single function instance. And then the serverless simulator uses those function instances to simulate a platform for a single user. And then we also have temporal simulator, which allows us to simulate the behavior of the system throughout time. This is a typical YOML diagram, YOML class diagram of our system. And as you can see, we have several classes, but our system has been designed with extensibility and ease of use in mind. It has an object-oriented design, and we use dependency injection to allow design validation of new design ideas. So any functionality that you want to change, for example, you extend the function instance and its behavior, and then you just inject your newly created function instance class into the platform, and it can help you simulate and see what happens when that type of function instance is used in a serverless platform. It also supports popular serverless platforms like AWS Lambda, Azure Functions, Google Cloud Functions, and IBM Cloud Functions. it has built-in tools for visualizing, analyzing, and verifying an analytical performance model, and can calculate PDF and CDF for custom state encodings, which help you in developing those analytical performance models. Now, we want to discuss some of the sample use cases of SimFaaS. So this is an example of the inputs and the kind of inputs and outputs that you can give and expect from this simulation platform. So, for example, in this example, any elements with a star next to their parameter name is an output of the system, and the other elements are an input to the system. And this is for simulating a typical workload on serverless platforms, which means a Markovian arrival rate and a Markovian service time. Although this is the process that we're simulating by default, all of these functionalities can be extended by the user and the developer that is using the system. So you can see that for a given arrival rate and warm start service time, cold start service time, and expression threshold, which is constant for any serverless platform that is currently in the market, you can try and see what will be the probability of a cold start happening to the new incoming requests. And this helps you keep an eye on the quality of service. It can help you see the probability of rejecting incoming requests, which helps you know the limitations of your system, so you can see when you will start rejecting requests because you don't have any capacity left in your system. It can give you the average instance lifespan, which is an important factor for the provider. And it can also give you average server count, which gives us the cost that the provider will be incurred. But at the same time, it can give you an average running servers, which gives you an indication on the cost of deployment, the cost of ownership for the developer that is trying to deploy this workload. And it gives you an idea on how much of the capacity is not being used on average. This is the sample code to generate those inputs and outputs. And you can see that after importing different parts of the library, after a few lines of code, you can generate simulations for a typical workflow, for a typical arrival process and a typical service time process. And it can give you some figures like this. So for example, on the right, we have the distribution of the number of instances throughout time. So what ratio of time do we have? 6 instances, 7 instances, 8 instances, or 9 instances. And we can see the average value here as well. And this gives us an idea on the amount of number of functions that are running in parallel and the number of functions that we have in our pool of resources. And using these values, we can predict in advance how much capacity does the database that supports this system need, and what is the cost that will be incurred by both the provider and the user. And you can also generate simulations like this, which give you your estimate for the average instance count, and by generating tons of traces, we can see the 95% confidence interval for these estimations. It can help you understand how confident are you in your simulation results. We can also do what-if analysis in this system. In this experiment, we assumed that we might be able to make the expression threshold adaptive, and these are the values that we are trying to use. So, for example, what if we can use any of these values for a given workload that you want to deploy? And this helps you calculate the probability of cold starts happening for any of those values for different arrival rates. And knowing this kind of behavior, you can predict in advance that if I were to change my expression threshold, how will it affect my quality of service? You can also calculate how it would affect your incurred costs and try to come up with a better trade-off for your system. Now, this brings us to the experimental validation of the system. So for experimental validation, we use AWS Lambda as an example, but as you saw, any part of the system is extensible. So you can try to simulate other platforms by just inputting their behavior and adjusting those values to any new platform. So the experiments were done on AWS Lambda. We used Python 3.6 runtime with 128 megs of RAM on the US East region. And we used a mixture of CPU and IO intensive tasks. The client that was making those requests was a virtual machine in Compute Canada Arbitos. It had 8 virtual CPUs, 16 gigs of RAM, and 1000 megabits per second connectivity with single-digit millisecond latency to those AWS servers. And we used Python for the client with in-house workload generation tool called PaxWG or Pax Workload Generator, which is open sourced and can be easily installed using PyPy. And we used the official Bottle3 library to communicate with AWS APIs, and we didn't use API gateways or any intermediary interfaces because we did not want the performance of those intermediary interfaces to affect our results, to get better and more stable results. These are some of the results that we got for our workload. This is the probability of cold start, how many of the incoming requests will end up having a cold start, which is a very important indicator of the quality of service. And as you can see, as arrival rates is increased, generally cold start goes down. And simulation and experiments are very well in tune, which shows that you can accurately estimate the probability of cold start for your system using our simulator in AWS Lambda. And we also have the average instance count, which generally is an indicator of the infrastructure cost incurred by the provider. And we can also, as you can see, get a very accurate estimate for this value. This is the average wasted capacity, and this is because of the way scale per request handles auto scaling. So since we don't allow any queuing in requests, we are creating more instances that is necessary, and we might have been able to get away with it if we allowed a little bit of queuing time for incoming requests. And this shows the average wasted capacity for the system, and we can improve these results by allowing adaptive expression threshold and generally doing a better task at managing these workloads. Now, this brings us to the conclusion of the talk. So SimFaaS is an accurate and extendable performance simulator for serverless computing platforms. It has the ability to predict important performance and cost-related metrics. So it can predict quality of service, you can calculate the average response time and things like that are very important for you as the developer who is deploying code to the platform. It can also be very useful to the service provider because the provider can use this tool to try out the new design ideas, see how it would affect the quality of service, the infrastructure cost before implementing them or before having to develop analytical performance models for them. It can be useful to the developers by helping them predict how their system will react under different workloads, what are the limitations of the system, how many arrival rates can be handled with our current system, and it can help them optimize their memory configuration to occur the minimum cost of service work that satisfies the performance requirements, because as you know, performance is not always linear to the amount of RAM that you specify for your serverless workload, and this tool can help them try out new things and see which one gives them the best results, minimum cost while still satisfying their performance requirements. And we also saw how making the expression threshold adaptive could give us better cost performance trade-offs, and we hope to see that in future in serverless computing platforms. Thank you very much.